Netflix, a global streaming giant, delivers petabytes of video content daily, handling billions of requests. To achieve this, they rely on a robust CDN architecture. What does it take to build a CDN capable of handling this insane volume while ensuring low latency and high availability globally? Here's what most engineers get wrong. They underestimate the complexity of global distribution and cache invalidation strategies. By the end of this video, you'll understand the key components and design choices behind a global CDN. Remember this 10 trillion number. We'll see why it matters when we discuss scaling. The secret is understanding the trade-offs between consistency and availability.
Let's define our scope. Functionally, we need to accelerate content delivery, protect origin servers, and mitigate DDoS attacks. Key non-functional requirements include low latency, sub 100 milliseconds, high availability, 99.99% uptime, and global reach. We'll support static content caching, images, CSS, JS, and dynamic content acceleration. Clarifying questions: do we need to support video streaming? For this design, we'll focus on web content. Do we need to handle authentication? Yes, we'll need to integrate with existing authentication systems. This will require a Web Application Firewall, WAF. We also need to support various content types and handle different request methods like GET, POST, and PUT. The API endpoint for content retrieval might look like this: get/API/v1/content/ID. We also need to consider the different types of content we'll be serving, such as images, videos, and documents. A common analogy is to think of a CDN as a vast network of post offices, each strategically located to deliver content quickly to users.
Let's estimate our scale. Assume 10 trillion requests per month, which translates to roughly 330 billion requests per day, or 3.8 million requests per second, RPS. If the average response size is 50 KB, we need to handle 3.8 M times 50 KB equals 190 gigabytes per second of bandwidth. Assuming a cache hit ratio of 80%, our origin servers need to handle 20% of the traffic, which is still 38 gigabytes per second. For storage, if we cache content for 30 days, we need to store approximately 190 gigabytes per second times 30 days equals 496 petabytes of cached data. These numbers drive our architecture. Stop. Think about this. These estimations directly influence our choice of caching strategy and infrastructure. This is where most people go wrong. They don't perform these estimations up front. We also need to estimate the number of edge servers required to handle the load. This is similar to estimating the number of delivery trucks needed for a postal service.
Now that we understand the requirements and scale, let's design the high-level architecture. A CDN fundamentally involves caching content closer to the user. We'll use a distributed architecture with edge servers deployed globally. We'll also use Anycast routing to direct users to the nearest edge server. Here's how it works. The client sends a request. The request hits a load balancer, which distributes traffic to API gateways. We separate the read and write paths for optimization. The write path handles content uploads and cache invalidation, while the read path focuses on serving cached content with minimal latency. We use Anycast because it allows us to route traffic to the closest available edge server, minimizing latency. Unicast doesn't provide the same level of global distribution and automatic failover. The API for uploading content might look like this: post/API/v1/content, content metadata. The load balancer uses a consistent hashing algorithm to distribute traffic across the edge servers. Consistent hashing ensures that when servers are added or removed, only a minimal amount of data needs to be reshuffled. Standard modulo hashing was considered, but it would result in a complete reshuffle of the cache on every server change. A key component is the rate limiter, which protects our origin servers from being overwhelmed by sudden spikes in traffic. A Web Application Firewall, WAF, is also crucial for filtering malicious requests and protecting against attacks. We use a WAF because it provides an additional layer of security, preventing malicious traffic from reaching our origin servers. Without a WAF, our origin servers would be vulnerable to various attacks, such as SQL injection and cross-site scripting.
Let's dive deeper into the core logic. Request routing is crucial. We use GeoDNS to route users to the closest edge server based on their location. This minimizes latency. When a request hits an edge server, it first checks the cache. If the content is present, cache hit, it's served directly to the user. If it's a cache miss, the edge server fetches the content from the origin server. We might be tempted to use simple TTL-based cache invalidation, but that can lead to stale content. Instead, we'll implement a more sophisticated cache invalidation system using purging. When content is updated on the origin server, a purge request is sent to the edge servers, invalidating the cached content. Content compression is also vital. We use Brotli compression to reduce the size of the content, improving delivery speed. For secure communication, we use TLS/SSL termination at the edge servers, reducing the load on the origin servers. The secret is, the choice of cache invalidation strategy significantly impacts the freshness of content and the load on the origin servers. Your interviewer will push back here. Why not use a push-based CDN? The answer is, push-based CDNs require more complex infrastructure and are less suitable for dynamic content. We use purging because it provides near-instant invalidation, ensuring content freshness. TTL-based invalidation can lead to serving stale content for the duration of the TTL. Another common mistake is not considering the impact of cache invalidation on the origin server load. A Bloom filter can be used to quickly check if a content exists in the cache before fetching it from the origin server. This is similar to checking if a package is in the local post office before sending a delivery truck to the central warehouse. The algorithm used for consistent hashing is jump consistent hash, which is known for its speed and minimal key movement on rehash. Jump consistent hash is an algorithm that distributes keys across a number of buckets, such that when the number of buckets changes, only a small number of keys need to be remapped. This minimizes disruption and improves efficiency.
Now, let's consider the data model. We need to store caching metadata, request logs, and security policies. For caching metadata, we'll use Redis, an in-memory data store for fast lookups. The schema includes the content URL, cache key, TTL, and last updated timestamp. For request logs, we'll use ClipHouse, a columnar database optimized for analytics. The schema includes the timestamp, client IP, requested URL, response code, and latency. Finally, for security policies, we'll use PostgreSQL. It supports ACID properties and complex queries. The schema includes rules for rate limiting, WAF, and DDoS mitigation. Pause and think, what's missing from this schema? We also need audit fields like created at and updated at for tracking changes. We use Redis because its in-memory nature provides extremely low latency for cache lookups, which is critical for CDN performance. Memcached was considered, but Redis offers more advanced data structures and persistence options. We also need to consider data lineage, tracking where the content originated from. We can use a Bloom filter to quickly check if a content exists in the cache. This is similar to tracking the origin of a package in the postal system.
Let's discuss scaling and performance. Caching is the cornerstone of our CDN. We use a multi-tiered caching strategy. The first tier is the in-memory cache on the edge servers, Redis. The second tier is a disk-based cache. Replication ensures high availability. We replicate data across multiple edge servers. Sharding distributes data across multiple servers to handle the massive storage requirements. To handle the 3.8 million requests per second, we need to distribute the load across multiple edge servers using global load balancing. This brings us back to the 10 trillion requests per month we mentioned earlier. To handle that volume, we need to continuously monitor our system and identify bottlenecks. We can use tools like Prometheus and Grafana to monitor key metrics such as CPU utilization, memory usage, and network traffic. Remember the 10 trillion requests? This is where that scale truly matters, requiring us to implement robust sharding and load balancing strategies. An experienced interviewer will probe, what happens at 10x scale? Here's the key. We'd need to dynamically adjust our sharding strategy and potentially introduce more caching tiers. We use consistent hashing for sharding because it minimizes data movement when adding or removing servers. Range-based sharding can lead to hotspots. We can also use a technique called cache stampede to prevent the origin server from being overwhelmed when a popular content expires. This is similar to having multiple distribution centers to handle a surge in package deliveries.
Reliability is paramount. We need to design for fault tolerance. If an edge server fails, Anycast routing automatically redirects traffic to the nearest available server. We also need to monitor our system continuously. We use Prometheus to collect metrics and Grafana to visualize them. We set up alerts to notify us of any issues, such as high latency or server failures. We can use PagerDuty to manage these alerts. Regular backups are also essential. We back up our data to a geographically redundant storage system. We should consider active-active versus active-passive setups.
Active-active provides better failover but is more complex. Here's the twist. Even with all these measures, unexpected network partitions can still occur, requiring us to implement robust reconciliation mechanisms. We use Raft consensus for data consistency across replicas because it's easier to understand and implement than Paxos. Raft ensures that all replicas agree on the same state, even in the presence of failures. We also need to implement circuit breakers to prevent cascading failures. This is similar to having backup generators and emergency protocols in a post office to ensure continuous operation.
In summary, building a global CDN involves trade-offs between performance, cost, and complexity. We chose Anycast for low latency, caching for performance, and replication for reliability. Potential bottlenecks include cache invalidation and origin server load. Next steps could involve implementing dynamic content acceleration and integrating with more advanced security features, such as a rules engine for fine-grained control over traffic. Remember, the key is to understand the requirements, estimate the scale, and design a system that meets those needs. A rules engine allows us to define custom rules for traffic management and security. This is similar to having a set of regulations that govern how packages are handled and delivered in a postal system.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.